Okay, thank you very much. So in my line of work, physics and astrophysics, we think a lot about the concept of scale. And what I'd like to, my main theme today is to convince you that thinking about the scale of a system, which I'll define a little more precisely in a second, is a way of understanding things without getting bogged down in the details. To my mind, it's the first way you should think about a system. And I'll give you some examples where you can learn absolutely amazing things just by thinking about scale. The examples will be from quantum physics and also from astrophysics. So what do I mean by scale? We often work with populations of things that are not all the same. People, trees, mountains, what have you. But they're linear dimensions, say, if we're talking about linear scales, size scales. They don't vary by orders of magnitude, right? People are meters in height, give or take. They're not, there are no 10-meter people, there are no tenth of a meter people. And the same can be said of other things. Mountains, I guess there are small things. At the small end of the scale, it becomes, I think, a matter of semantics, what you call a mountain or not. But the highest mountains are about 6 miles high, I think. There are no 60-mile-high mountains. That's telling you something important about what makes mountains. So let me begin with some examples from quantum physics. You don't need to know any quantum physics. The idea here is something called dimensional analysis. In many areas of physics, there are fundamental constants that appear. In quantum physics, the fundamental constant is Planck's constant, h. This is h bar, which is h divided by 2. In electricity and magnetism, there are basically two constants. One is the fundamental charge on the proton or electron, and 4 pi epsilon naught is essentially a way of defining units. And here's me is the electron mass. So if we think of atoms as electrons bound by electrical forces to nuclei, we ask ourselves, there ought to be a Planck's constant in there because we're doing quantum physics. There ought to be some kind of charge in there because we're using electrical forces, and we're dealing with electrons, so the electron mass should appear. And what you do is to say, how can I take these constants and make something with the units of length? And this is basically the unique answer. It comes out to be 0.529 times 10 to the minus 10 meters, or about half an angstrom. And lo and behold, that's the size of a hydrogen atom. Think about it. I didn't need to know anything about quantum mechanics to get that answer. But by doing that, if I were the first person to do it, I would know that atoms had sizes of angstroms, or tenths of nanometers, as opposed to the size of beach balls. You can play the same game with energy. Oh, here are atomic radii sort of confirming what I said. Little hydrogen is up there at the top at half an angstrom. You can see that the atoms are not all of the same size, but they don't vary by more than maybe 2 orders of magnitude, maybe a little less than that. Coming back to energies, you can say, let me take the same constant, set of constants, and make something with units of energy. And the top there is the unique answer. As you can see, I'm a theoretical astrophysicist. Oh, okay. The answer is a number of order 10 electron volts. The minus sign is there because that's actually the binding energy of hydrogen. That number is exactly equal to the binding energy of hydrogen, the amount of energy that it's required to take it apart. And if you had done this for the first time, at this point you would know that the energy levels of atoms are separated by electron volts, not thousands of electron volts or 1,000th of an electron volt. Okay, that's what I've just been describing is called non-relativistic quantum mechanics because the constants we used didn't have anything to do with relativity in them. The fundamental constant for relativity is c, the speed of light. So let's play the same game. If we do that, we get the relativistic theory of It depends on what system you're talking about. I picked photons and electrons because it's a very historically important example. The length scale comes out to be this number. And as we go to higher energies, it turns out, you can see the fundamental energy. This is me c squared, the electron mass times c squared is the rest energy of the electron, the amount of energy you could get out if you turned it into pure energy. It's much higher than the energy scale for non-relativistic quantum mechanics. And at this point, we would know that QED describes experiments where the energies of the photons and electrons are like millions of electron volts. And we can keep playing this game. Suppose I want to put gravity together with quantum mechanics. This is the frontier right now. Nobody, in my opinion, knows how to combine quantum mechanics with gravity. How would we do that? Well, we know gravity has to appear there. So Newton's constant, which describes gravity, is capital G. We play the same game, and we get this absurdly small length. The radius of a proton is about 10 to the minus 15 meters. So this is a length scale which is 20 orders of magnitude smaller. And we get a very large energy. The rest energy of a proton is 1,000 electron volts. This is 13 orders of magnitude larger. Sorry, no, it's more than that, of course. This is 1 TeV, 1 tera electron volt is 10 to the 12. So this is 10 to the 28 electron volts. The proton rest mass is 10 to the 3rd electron volts. No, 10 to the 9. So this is 10 to the 19 proton masses. More importantly, you all know about the Large Hadron Collider, the particle accelerator in Switzerland and France, which is just coming back online. When it's fully operational in a month or two, it will accelerate protons and antiprotons to energies of 10 TeV. If you had done this little calculation, you would know at this point that the Large Hadron Collider is not going to tell us anything about quantum gravity. Which is probably good. It has its own agenda. I didn't need to know anything about string theory or brane theory or quantum loop gravity or so on to understand that the energy scale for quantum gravity is this. So I hope that's by way of convincing you that very simple thinking, the big view, what is the natural scale, whether in terms of length or energy, can tell you an enormous amount about what system you're dealing with. Okay, I'm actually an astronomer by trade, so let me give you an astronomical example. You may know that one of the most vibrant subjects in astronomy is the discovery of planets outside the solar system called exoplanets. And here's a histogram. There are now about 1,500 known confirmed exoplanets. There are another 1,500 that are waiting confirmation. So a lot of the actual data appear here. And what's plotted is the number of planets as a function of its size measured in the, units of the radius of Jupiter, the biggest planet in our solar system. How many length scales are there in this, length scales are there in this plot? 1, do we hear any other opinions? 2, there are 2. There's this histogram. You might think that this is noise in the data. It's not, because these numbers are actually quite large. You would expect fluctuations of something like the square root of whatever number you have here. So there's a population here. Those are planets like Jupiter, which are basically self-gravitating balls of gas held together by their own gravity. And then there's this spike here. Anybody guess what those are? Super-Earths. They're rocky planets. Now, we don't actually know what determines this. So this histogram just tells you what the scale is. It's a very important and controversial question. You know, what sets the limit on the size of rocky planets? Is it limited, for example, by the amount of rocky materials that a young solar system has available to make those planets? And I'll talk a little bit more about what makes gas giants next. Gas giants are giant planets like Jupiter, which are mostly or entirely made out of gas as opposed to rocky materials. How am I doing for time? But does that mean 2 minutes or? Okay. This is a figure which describes stars. It's a very famous kind of figure called an HR diagram, which plots things that probably are not of primary interest to us today. But for each star, there's a dot here which gives the surface temperature of the star going increasing from right to left for historical reasons, and the power output or luminosity of the star measured relative to the sun and on logarithmic axes. And the original astronomers who made a diagram like this realized that all of the normal stars, by which I mean stars like the sun that are burning hydrogen in their cores, lie on a narrow band. It's not a line, it has some width, which is called the main sequence. You can figure out from the temperature and the power output what the radius of the star is, and you can see there are dashed lines here. So normal stars, stars in the main sequence, have radii between 1/10 of a solar radius and 10 solar radii. Now, understanding why that's so theoretically is much more involved than making dimensional combinations of fundamental constants. That can only be done with computer models. But the computer models reproduce all of these results. But we can ask the following question. A star is, for our purposes, a self-gravitating ball of gas, by which I mean a ball of gas held together by its own gravity, which produces light via nuclear reactions. Now, the nuclear reactions part is not essential. I'll come back to that in a second. But let me ask you the question. How big a ball of gas would you need to make a ball of gas held together by its own gravity? You could imagine doing this by taking balloons and filling them with gas. And let's assume, for the sake of argument, that we can adjust the temperature of the gas whatever way we please, and the density of the gas inside however we please. So if I buy a helium balloon at my local whatever store, and I pop the balloon, if it's self-gravitating, there'll be a ball of gas that just kind of stays there. Is that what's going to happen with an ordinary balloon? No. Now, why is that? There's not enough gravity to hold it together. When I pop it, the helium atoms have enough velocity that they can leave, and the gravitational attractions between each helium atom and every other helium atom are not enough to stop it. There's another way to look at this in terms of energy. A system will be bound if its energy is negative. That means you have to put energy in to take it apart. And a good example of that would be a bowling ball at the bottom of a well. In order to disassemble that system, you have to put energy in to lift the bowling ball out. Now, in self-gravitating systems, there are two kinds of energy. There's the kinetic energy associated with the random motion of the atoms. That has roughly the same value for each atom and increases with the temperature of the gas. And then there's the other kind of energy, which is the energy associated with gravitational attraction. That's negative, and you get a contribution from each pair of particles. So I have two contributions, a positive contribution that's proportional to the number of particles in the system, and a negative contribution that's proportional to the number of pairs, which is in turn proportional to the number of particles squared. Positive energy proportional to number of particles, negative energy proportional to number squared. How do I make a system with negative energy? Increase the number of particles or decrease it? Increase it, because n squared increases faster than n to the power 1. So that tells me right away, if I make a ball of gas big enough, it will be gravitationally bound, and that sets the scale for stars. There's a mass associated with that called the Jeans mass, or what's plotted here, what's illustrated here is not the critical mass, but the critical length. The details aren't terribly important. Uh-oh. I think I've broken it. The critical length is proportional to the speed of sound, which increases like temperature to the 1/2. So if you want to make a small ball, you have to have a cold gas. And it's inversely proportional to the mass density or number density to the 1/2. So if you want to make a small gravitationally bound object, you want a very dense object with lots of particles per cubic meter, say. What you're looking at, oh, I have two panels here. So how do stars form? What you're looking at here is an image of the sky toward a region of our galaxy where there's lots of gas. The pink stuff is actually light which is reflecting off that gas back into the camera, making kind of a background. And this object here is a more or less random place where the density is quite a bit higher than the surroundings. And if this density, if this object grows bigger than the mass corresponding to the Jeans length, it will become gravitationally bound. I won't put the numbers in front of you because that's too much numbers for one talk. But if you take the density of this gas and the temperature, compute the Jeans length scale and then the Jeans mass, you get a mass of a few solar masses, roughly the mass of stars. So now we understand where the masses of stars come from. Going back to the main sequence, we can also ask the question, the main sequence cuts off at a mass of about 0.08 solar masses. And that's actually easy to understand because if something is gravitationally bound, but if it's sufficiently small, it won't be hot enough in the center to have nuclear reactions. You need about a 10 million degree plasma for hydrogen burning reactions. So this cutoff is more or less determined by nuclear physics. At the upper end of the main sequence, we don't see any stars bigger than about 10 solar radii, which translates to mass increases from low mass down here. This is about 0.08 solar masses. At the top, people argue whether it's 150 or 200 solar masses. We also understand that physics. Stars that are too massive actually blow themselves apart. This is a Hubble image of a famous star called Eta Carina. It's producing so much light. It turns out that the larger the mass, the more light a star produces. And the light goes like mass to the 3rd or 4th power. So it's not a linear effect. Eta Carina is a star with a mass of perhaps 120 solar masses. And it's producing so much light that the photons, the particles of light, are actually lifting off the outer layers. So it may, we don't know for sure, it may actually evaporate itself and disappear, or it may go through some other changes. It depends on some physics that I don't want to burden you with today. Time? Time to stop? Okay, all right. Thank you very much. I have some extragalactic examples too, but I think we've done enough for one day. But please give some thought to looking at whatever system you're doing, whether it's biological, astronomical, chemical. Think about the scale of the system you're dealing with as a way of simplifying, freeing yourself from the details. Again, thanks for your attention.